In this 10 minutes, let me take you to the space of bilinear form and let's take a peek to their structure. So first, to follow along, you need to have a general idea about matrix dot product. You can check them at 3b, 1b, he covered them pretty well. It will be a link in the description. Now, to understand bilinear form, we need first to talk a little bit about linear form. As linear in the name suggests, it has the same property of linear transformation, but in linear form you restrict yourself with the landing spot. It must always map a given vector space E to a field of scalars, in most cases either R or C. In the end, it's just a particular case of linear transformation. Now we are ready to talk about bilinear form, so without further ado, let's dive right into it. Of course, the first question that pops up to your mind is what's the difference? Linear form, bilinear form. Simply, it's an upgrade. Instead of taking from one vector space, it will take from two and map it as usual to the field. In addition, it's linear in each argument, as you can see here. It's a bit complicated, that's alright, think of it this way. B operate as two linear form. Take any vector x from E, fix it in the first argument, you'll get a brand linear form over the vector space E. Also, the same apply if we fix the second argument. This is nice and all, but with that alone, it's not obvious what's B actually doing to our vector space. So with our knowledge of linear algebra, let's see if we can understand what's going on there. Now, since we are in a vector space, every vector in our view can be written as a combination of the basis vectors. Apply that to X. Now fix Y and treat B as linear form as we see earlier. Here we put Y again and repeat the same thing. Now it's time to clean. Now repeat the same with the second argument. Dude, it was really a long journey, but if you did everything right, you should end up with a messy formula like this. So if you work before with that product, it's actually a nice form to work with. Let me show you. Forget about the n dimension and let's just work with 3. Let's start with splitting the sums. With this arrange, you can see the formula of the dot product between the two vectors. Let's call the first one x and the second z. Here, if you look closely to the component of z, you can see clearly the matrix transformation of y. Now we have an idea on how B operate in the vector space, and we can now encapsulate B in a nice matrix like this. So obviously the next step is applying that and see B in action. B, as we see, take the first argument x, fix it in the space, and by linear transformation sending y to its proper image. Then projecting it to the line passing through the vector x, and multiplying the length of this projection by the length of x, then give you the result. So that's, my friend, is the story of how the function b maintains the linearity properties with two input. So that's it. I think this is enough for an introduction, but before I end this video, let me leave you with a nice question. Does the order of the argument matter? Meaning bxy equal byx? In other words, fix x and project the image of y, then multiply the length. Is it equal to fix in y and project the image of x with the same linear transformation and multiplying the length? So think about it. Till the next video.